Welcome to our another new video series. This time we're looking at chapter 7.2, and we're going to look at the first section of that, which is binding energy. And overall, chapter 7.2 is looking at nuclear reactions. And this is a pretty fun unit. It is probably one of my more favorite units in the study of physics because we get to look at one of the very famous equations, E equals to mc squared. Associated with probably, again, one of the more famous scientists in physics and probably all of science, Albert Einstein. So this is Einstein's, Einstein's famous equation here. Oh, I don't know why that keeps coming up. I guess because I'm trying to edit that. Okay, Einstein. All right. Okay, so first off, we're going to start off with a basic definition. So what we've got here is we're trying to redefine the kilogram into a new unit known as the unified atomic mass unit. Okay, so sometimes we just say U, unified atomic mass unit, but that's because we're dealing with masses of such a small scale that we want to get rid of all of this 10 to the power of 27. That's what scientists want to do. So because they often talk about like a neutron or a proton, and they don't want to always talk about 10 to the power of minus 27. So they're redefining something as a U, or unified atomic mass unit, AMU. Sometimes you might see that AMU is also quite common. So the AMU, or the U, unified atomic mass unit, was defined using carbon-12, or the most common version of carbon that we have here on Earth. And if you look at that, it's 1/12 the mass of carbon-12, which actually means, if you think about that, there's 12 nucleons. And if it's 1/12, it's roughly one nucleon, is what one AMU is supposed to represent. So it's either one proton or it's one neutron. Okay, and this is in your data booklet. Sorry, I forgot to mention that. This is also in your data booklet as well. And you might notice, this is kind of interesting. You might wonder, why would a proton or a neutron not be more closer to one? Why wouldn't at least one of these, maybe the neutron should have been one? We're going to get into why that is a little bit later. So, oh, sorry, I forgot to mention, there are some really kick-ass videos in the beginning of this chapter. There's two videos, actually, if I remember correctly, in 7.2.0. Really encourage you guys to watch that. Either pause the video now and watch it, or you can watch it afterwards. Really, really good stuff. And so let's continue on. So how does E equals to mc squared work? So this is slightly touching on the stuff that's going to be in that video, and we'll get into a little bit more of why and how this works a little bit later. But the whole idea of E equals to mc squared is that it's telling us that the amount of energy that can be generated from a certain mass, we need to multiply that by the speed of light squared. So really, what that's really telling you is that you don't need a lot of mass to get a lot of energy, if you can fully convert all the mass into energy. So as sort of something for you to think about and consider is one single 4 grams, not kilograms, a glass marble of 4 grams has the energy to vaporize water in 50 Olympic-sized swimming pools. That's a lot of water, okay? And that's assuming the water wasn't necessarily close to boiling point. That was at 20 degrees Celsius. So it's enough to heat the water, completely vaporize it, if you can convert all of that mass into energy. And so you can see the scale that as I mentioned earlier, you don't need a lot of mass to get a lot of energy, okay? So it's on a crazy scale, and that's how that also explains how nuclear reactors, right, a tiny little box inside a submarine, can generate the entire energy for a whole submarine. And that's pretty crazy. So nuclear reactors inside submarines. Feel free to do a quick little search on that. So further on is that we want to also look at another way, because dealing with E equals to mc squared, we also have to convert from kilograms into AMUs, and then we have to deal with the speed of light. So we're dealing with a lot of different constants, and what this is showing us is that we can actually simplify that. Okay, so so here we've got a typical example. We have the mass of the mass for one AMU or one U, and we're trying to convert that into the equivalent energy version. So this is really E equals to M, right? And so rather than kilograms, sorry, we've got kilograms here, but one U is also, it's all mass really, U and kilograms times C squared. And so we multiply it by the speed of light. So this is essentially 3, but this is the more accurate version of the speed of light, 3 times 10 to the power of 8, or 2.9979 something squared. And then we get this measurement in joules. Okay, so you might remember from our other unit, we don't like things in joules, we want things in electron volts. And so then we have to do another division, which you might remember, divide by 1.6 times 10 to the power of negative 19. So it seems like a lot of work. We have to work with the speed of light. We have to work with this other constant here to convert joules into electron volts. And so what this is really telling us is that this is giving us the shortcut, okay? So E equals to mc squared, E equals to mc squared, right? So that's what this really is. And what it's telling us is that if we have something that's close to that is a unified atomic mass, then we can simply just multiply by this number and we'll automatically get that result in electron volts. So it gives us a quick conversion from mass into energy, but this will be in electron volts, and this could be given in U's instead. So we're dealing with the atomic levels of mass and energy directly by using the single constant. Okay, so we're eliminating 2 constants as a result. Okay, so here we have an example to help us illustrate that. The energy of a proton can be calculated by its unified atomic mass, and we multiply that by the speed of light. Okay, so to show you what's going on is that 1 U can be replaced with this. Okay, that's exactly what we saw here, right there. Okay, and so we're replacing the U directly with this, and then what you're actually seeing here is that the C, I'm just going to use a different color, C carries on over here, and thankfully the C's cancel. Okay, so we've eliminated U and we eliminate C. That's what I meant. Okay, so we're destroying 2 constants with a single one. So we multiply the 2, and that's how much energy it has. Okay, mega electron volts. Don't forget, this is 938.3 times 10 to the power of 6 regular electron volts. Okay, so mega 10 to the power of 6. Okay, this example is asking us to find the mass of a neutron and electron in MEC squared. Now, again, if we look at what's happened a little bit earlier, MEC squared, that's exactly what was going on here. So really, MEC squared and U are the same things, okay? And that's what we're trying to do here. So what we're really saying here is that the energy of the mass of a neutron, sorry about that, and the mass of an electron can be calculated by looking at its the data booklet piece right here. So we're taking these values here, neutron, 1.008665. So 1.008665, multiply that by our constant, and we automatically get our MeV over c squared. Okay, so likewise with the electron, okay, this you can look up in your data booklet. I'm not going to scroll back up. Multiply that by 931.5, and you'll get your value in mega electron volts, c over c squared. Okay, and of course, this could be converted back to U. Okay, so next up, so the first little bit was sort of all about how does this E equals to MC squared work. We are now looking at mass defect. So here's sort of the interesting bit that, again, if you want to pause this at right now and watch the two videos in 7.2.0, the two videos there, this is going to explain that, or you can watch it after, as I said. Carbon 12 has that much U. So if you remember, both the neutron and the proton and neutron were a little bit more than 1 U. So how is it that the combination of all of them is less than that? What's going on here? So short little explanation, which we'll get into a little bit later, is that some of that mass has been converted into energy. And I think we talked about this earlier. This is sometimes, it's related to the strong atomic force. This is going a little bit beyond what you need to know in this course, but this has to do with the strong atomic force. And it also has something to do with gluons. Okay, these are with quarks and stuff like that. But again, this is going a little bit beyond right now. But essentially, the energy is converted. The mass is converted into energy to hold these guys together. That's what's going on there. So to really see that 6 protons and 6 neutrons is actually about 12. It's a little bit more than the sum of the 6 nucleons altogether. And so the difference of those values is known as a mass defect. So let's do a quick little calculation here. So we're going to calculate the mass defect for a helium nuclei, or an alpha particle. And the helium nuclei, we're given that the helium, a regular helium atom has this. So we need to subtract 2 electrons from that. So here is our 2 electron calculation there. So we're subtracting this number. Okay, and we end up with this value. So this is now our alpha particle mass, whereas this was the entire helium atom. Okay, and that's now a full alpha particle now without the electrons. No electrons. And so to kind of finish this off, we have, these are the individual values of our 2 protons and our 2 neutrons. So we're comparing this value with that one. Okay, so just to see that, kind of copy and pasted 2 down here. So if you want to reference that, okay. And we end up with a difference of 0.030377 AMUs, or U. Okay, so the binding energy of a nucleus can be the energy required to separate the individual parts, or the individual nucleons individually. Okay, so if you had a proton, the neutron, okay, it's that energy required to separate these guys. And what's you'll find a little bit interesting is that each of them actually has their own different amounts of binding energy. And so to find the binding energy, we'll get into that a little bit later. Binding energy is the mass deficit multiplied by the speed of light squared. Okay, so thankfully we don't have a huge mass deficit. So multiplying by the speed of light doesn't give us crazy amount of energy, but it is still quite significant. Okay, we're at 92.16 mega electron volts for the mass deficit of carbon-12. So the binding energy for one carbon atom is 92.16 mega electron volts. That's one single atom. Okay, so you can imagine if we had a chunk of carbon, right, which would have millions of atoms inside of it. Okay, how much energy that could release. Okay, so as I mentioned a little bit earlier, is that it's actually the individual parts. So the binding energy of each individual nucleon. So for one single, so maybe it's for one proton or for one neutron, it is this much energy. Okay, so this is for one nucleon. Okay, third example, calculate the binding energy per nucleon of our helium atom. So we've done this calculation a little bit earlier. We're just going to steal that mass deficit. So you can reference back up here for our calculation right there, right? So that was our alpha particle. And then, so that's the binding energy just inside the nucleus. So we're taking that energy, multiply it by 931.5. We get 28, roughly, mega electron volts. So per nucleon, we then have to divide it by 4 to get about 7. Okay, last little bit is something that you are going to find inside of Cognity. This curve shows you what's sort of interesting is that the number or the binding energy required has a pretty sharp increase from hydrogen to helium, and then it quickly starts to peak at carbon. Okay, so we're reaching pretty high right now, and then it's sort of peaking around Ni, and I think that's nickel. Okay, and then it starts to drop after that. So any elements that are heavier than nickel, the amount of binding energy actually starts to decay, and you can see uranium 238 is roughly about the same amount of energy as carbon. Okay, so this is definitely, this curve is something that you do want to know, like this massive spike up, okay, and then gradually going down, and then one of the peaks there being nickel, which is element 62. That's something you definitely want to remember. And also carbon and uranium, roughly the same. Okay, thank you guys for watching, and we'll see you next time.